Now, once we understand the full picture of universal gravitation law by Newton with Cavendish's discovery of G constant, right? Now we can actually apply what we know and finish or figure out things more accurately and precisely. Okay. Um, so how do we apply what we know with the following? Okay, so we're going to try to utilize what we know. Now, what I recommend is, I think I already told you to print this out. Remember this sheet when we were using the Kepler's law? You may need to use this sheet in order to, use some of these constants as well as some of these, formulas. It's good to know. So it's probably good to have this thing next to you when you're working on this. All right. So let's get this started. Now, here, assume Earth is moving in a circular orbit around the sun. So let's visualize this. So let's draw sun right here. Our sun. Sun, Mr. Golden Sun, please shine down on me. Right? Mr. Sun, Mr. Golden Sun, hiding behind that tree. When the children are asking you. That's my sun. Right? Now, Earth is going to be going around the sun. Okay, so here's our planet Earth, our blue marble, right? Some trees. Okay. Now, when this thing is going around, I want to know how fast this Earth is going around the sun. Now, the average distance between the Earth and the sun is measured from the center of the sun to the center of the Earth. Okay? So the distance, mean radial orbit, is basically this. Okay? This is the mean radial orbit. So this is R. Okay? So they want us to find out how fast the Earth is moving in miles per hour. Well, we could do this without using too much of physics. I'm going to show you how to do this two ways. One way is the straightforward way because we know the Earth is going in a circular path around the sun, right? Circular path. Because very close to circle, even though it's supposed to be elliptical. But the eccentricity between the two foci are so close to one another, it's almost a circle. Okay? So we can say the speed of Earth is equal to, right? Speed of Earth is equal to the distance the Earth travels, divide that by time it takes to travel that distance. The distance it travels is basically the circumference, which is 2 pi r. And the time that it takes to go once around the sun, we know it is 1 year. Does that make sense? Right? That's pretty straightforward. So let's think about what the distance is. So V Earth is equal to, right, 2 pi r. So 2 times pi times 1.5 times 10 to the 11th meters. Divide that by 365 days. Okay? So if you work this out, Well, let's convert this days into seconds. Well, we could do that later, I guess, if you want to. So here we got 2 times pi times 1.5 EE11th. This is equal to 9.425 times 10 to the 11th. Divide that by 365 times 24 will give me hours, right? So meters. So what's 364? 365 times 24. That is 8,760 hours. So since they want this in miles per hour, we have this bottom part done already. But we need to convert the top into miles. So my speed of Earth is equal to, right, 9.425 times 10 to the 11th meters. I want to convert that into miles. So in 1 kilometer, or 1,000 meters, and in 1 mile, there are 1.61 kilometers. So notice how the meters can cancel out and kilometers can cancel out, right? Giving me in miles. So basically, if I multiply that 9.424 EE 11th, if I multiply or divide that by, I should say, 1,000, and then divide that again by 1.6, I should get miles at the top. So that is 585389935.4 miles per 8,760 hours. So if I divide that by 8,760, I get 66,825.3 miles per hour. That's pretty darn fast. You'll definitely get a speeding ticket, right? It's like 1,000 times faster than legal speed limit in the highway. Yeah, so that's pretty. We're moving pretty fast. We're moving pretty fast. Now we didn't really have to use any physics to solve this. We just used our intuition and what we know, what's available to our, mind, right? Well, how do we use now physics, what we know in gravitation? Now we know the Earth is being pulled towards the sun as much as Earth is pulling the sun. So there's gravitational interaction between the sun and the Earth. Well, even though the Earth wants to go straight tangentially, the sun is saying, no, you're not, right? No, you're not. It's constantly pulling the Earth towards the sun all the time. Okay? So there is a gravitational force pulling, this gravitational force pulling the sun, right, towards the center, and we call that F big G. Okay? So another way of doing this problem is we know that sum of all forces, and I've noticed this thing is going in a circle now, so the net force of circular motion is equal to MAC. We learned that. And we also know that the net force in a circular motion, there's only one force acting in a radial direction, and that is the FG. F big G. This is big G compared to the small g is different, right? Small g is m times 9.8, right? Where this big G is what we just learned about in Newton's universal gravitation. So since these two net forces are equal to each other, these two must also equal to each other. And since direction of AC is positive, FG, which is also in the same direction as AC, so they're both positives. So MAC is equal to F big G. This mass here is the mass of the Earth, because Earth is the one that's going around in a circle. So here, the mass of the Earth times V squared over R is equal to G times the mass of the Sun times the mass of the Earth divided by R squared. Look what happens to the mass of the Earth. The mass of the Earth, boom, boom, gets canceled out. And one of the R's get canceled out at the bottom. So the speed of our Earth going around the Sun happens to be just the square root of universal gravitation G, constant, times the mass of the Sun divided by the distance. Therefore, if we were to put all this together and start putting in the numbers, G is 6.67 times 10 to the negative 11th. Mass of the Sun is given to us as 1.99 times 10 to the 30th kilograms. So the mass of the Sun is 1.99 times 10 to the 30th. You could use 2. R, which is 1.5 times 10 to the 11th meters. So R is 1.5 times 10 to the 11th. So if you work this whole thing out, what you get is, you should get something like square root of, I'm writing this so you guys can check your calculations, 488,666.7. So if you take a square root of that number, you should get 29,747. But what's the unit? Well, unit's going to be in meters per second. Because this is in meters, this is kilograms, right? I'm sorry, newtons times meters squared per kilogram squared. This is also in meters, so you're going to get meters out of this deal and meters per second, because Newton has seconds in it. So to convert this now into miles per hour, all we have to do is multiply, well, there's 3,600 seconds in 1 hour, and there are 1 kilometer is equal to 1,000 meters, and 1 mile, there are 1.61 kilometers, right? So notice how the seconds will cancel out, right? And then the meters will cancel out, and then kilometers will cancel out, giving me miles per hour. So if you work this out, you'll get something like 66,515.13 miles per hour. Now the difference is, because of all these other carryovers in different decimal places, I think makes the difference. Okay. Also, if you divide this by 365.25, because the leap year, this will make it smaller as well. Okay. So yeah, so it is pretty close. It's pretty close. All right. So that's the other way to do using universal gravitation. All right. All right. Good. Next, let's calculate the force of gravity on a spacecraft that is 12,800 kilometers, which is 2 Earth radii. So if this, you know, 12,800 kilometers, which is really equals to, right, 12.8 times 10 to the 6 meters, and that is actually 2 times the radius of the Earth, they're saying. So let's work with what they give us. Okay, let's work with what they give us. So that is actually the altitude. This is the altitude. And altitude is measured from the surface of the Earth to where the spacecraft is. Okay? So that's good to know. So let's visualize this. Let's draw some pictures. So here's our Mother Earth. Right? And our Mother Earth will have radius of 1 Earth radius, like so. And the spacecraft is way out here. That's the spacecraft. And the altitude, this is the altitude, is equal to 2 times the radius of the Earth. So our orbiting distance or orbiting radius r is equal to 3 times the radius of the Earth. Okay? So the radius of the orbiting radius is equal to, right, basically radius of the Earth plus the altitude. That's very important. Okay? So now that we know that, let's figure out the force of gravity on the spacecraft. Okay? So what is R? Then R is equal to, right? Well, we know if this is twice the radius of the Earth, we can say the radius of the Earth is equal to 6.4 times 10 to the 6 meters. Is that okay? This is just half of that. All right. So it's 3RE, which is equal to 3 times, right, 6.4 times 10 to the 6, which is equal to 19.2 times 10 to the 6 meters. That's our orbital radius. I could make it 1.92 times 10 to the 7th, but I just want you to get used to that times 10 to the 6, which is a million. You know? All right, so we could say now that Fg, this is big G now, is equal to G times the mass of the Earth times the mass of the satellite, divide that by r squared. So what is the gravitation between the two? Well, now it's just plug and chug, really. It's all math, right? It's all algebra from here. So the gravitational force acting between the spacecraft and the Earth is 6.67 times 10 to the negative 11th newtons times meter squared per kilogram squared. And you'll see that it will all cancel out to just newtons. Then, mass of the Earth. Mass of the Earth is basically given to us as 5.97 or 6.0 times 10 to the 24th kilograms. That's the mass of the Earth. Times the mass of the spacecraft, which is only 1,400 kilograms. Whole thing divided by R, which happens to be 19.2 times 10 to the 6th. You have to do quantity square on that thing. So if you do your calculations correctly on your calculator and punch it in correctly, okay, you should get 1,519.9 newtons. Now, just want to show you the significance of this. Instead of plugging in this R value as 19.2 times 10 to the 6, let's put this as 3RE. Okay? So, alternate solution. Okay? So, here, if I were to say FG is equal to, okay, 6.67 times 10 to the negative 11th times 6.0 times 10 to the 24th times 1400, divide that by 3 times the radius of the Earth quantity squared. That is, right, 6.67 times 10 to the negative 11th times 6.0 times 10 to the 24th times 1400, divide that by 9 RE squared. We know this is this, right? So let's do this. I'm going to factor this 9 out. So 1/9 times 6.67 times 10 to the negative 11th times 6.0 times 10 to the 24th times that over 6.4 times 10 to the 6 squared. Let's calculate this. What do we get? I get 1/9 times, when we calculate this, we get 6.67 EE negative 11th times 6 EE 24th times 1400, right? Divide that by 6.4 EE 6 squared. Okay, so I get something like 13,678.7 times 1/9 newtons. That's my FG. Now, what if I were to put this spaceship on Earth, right? If I put the spaceship on Earth, what would the FG be? That would be this, wouldn't it? Because the radius of separation is just the radius of the Earth, right? Here's the magic. Ready? What is the F small g of the spacecraft on surface of the Earth? That is simply nothing more than 1,400 kilograms times 9.8. And what is that? Well, 1,400 times 9.8. Look how close they are. So this is actually the weight of the spacecraft on the surface of the Earth, and this is the same thing. So when you're this far out, 3 times the radius of the Earth, right? Guess what? It's 1/9 of whatever that object is on Earth. So if it's doubled, it'll be 1/4. If it's tripled, then it'd be 1/9. What would happen if you do 4 times the radius of the Earth? What would that be then? 1/16 of this. So further you go out, the gravitational force becomes weaker and weaker and weaker as it goes out. And it gets weaker by 1 over the radius squared. The inverse square law, that's what it means. Right? The inverse square law means when you go out twice the distance, it'll get weaker by 1/4 as much. Right? If it goes 3 times the distance than original, then you get 1/9 as much. 4 times the distance, 1/16 of the original force. Okay? And that's the inverse square law. So this is only like 90 some percent, of original. Like, I mean, not 90%, like almost 1/10, a little more than 1/10 of. All right. All right. So let's take a look at number 13. Number 13 states, okay, a hypothetical planet has mass 2.5 times that of the Earth, but the same radius. What is the acceleration due to gravity on the surface? So if I have a hypothetical planet and I put you on it, I'll put Aiden here with her designer Gucci spacesuit again. Right? Right? She's wearing her designer Gucci spacesuit. They're very expensive. It's made in Italy by Chinese immigrants. anyway, she will feel weight on the surface of this planet. And this weight will be simply calculated as F small g. And this F small g is literally mass of Aiden times g. Right? That makes sense, right? She's on the surface, so she has to be mg. Her weight should be mg. And we know the distance of separation between that planet and Aiden is same as the radius of the Earth. So she's also feeling this big Fg, which is same thing as G times the mass of the planet times mass of Aden. Oh, I should put give her a capital A instead of small a, right? Divide that by the radius of the planet squared. Well, darn it, these two have to equal to each other, but they're same gravitational forces, right? Because she's on the surface, and this is how you calculate the gravitational force on the surface, right? So the radius of the planet is equal to radius of the Earth. So let's set them equal to each other. So mass of Aden times G must equal to G times the mass of the planet times mass of Aden. Divide that by the radius of the planet squared. Well, look what happens to mass of Aden. Boom, boom. Her Gucci spacesuit doesn't matter. All right. So G, which is the acceleration due to gravity on that planet, okay, must equal to this big universal constant G times that mass of the planet, divide that by the radius of the planet squared. But we know G doesn't change, but the mass of the mystery planet is 2.5 times the mass of the Earth. Divide that by, well, the radius of that planet is same thing as the radius of the Earth, therefore RE. So if I factor this out, this 2.5 out here, and then G times the mass of the Earth divided by the radius of the Earth squared, what is this? What do you think this is? Well, let's figure it out if you don't know what it is. Here it is. So 2.5 times 6.67 times 10 to the negative 11 times the mass of the Earth, which is, what's the mass of the Earth? I'm going to say 6 times 10 to the 24th times. Radius of the Earth is 6.4 times 10 to the 6 quantity squared. Don't multiply this by 2.5 yet. Just do the inside the parentheses first. Let's use the PEMDAS, right? Please exhume my dead Aunt Sally, right? So if we do this inside the parentheses first, what do we get? So it's 2.5 times this parenthesis. So here we get 6.67 EE negative 11th times, right? 6 EE 24. Divide that by, right? 6.4 EE 6 squared, right? Squared, and I get OMG. Does that look familiar? That looks like acceleration due to gravity of the Earth, 9.77 or 9.8. So all this mess is that. All this. So the acceleration on that planet, acceleration due to gravity on the planet is just that times 2.5. And we get G for that planet, the mystery planet, is 24.4 meters per second squared. So Aiden's going to feel very heavy. I mean, if she weighs 100 pounds here, On that planet, she's going to feel like 250 pounds with that Gucci spacesuit, maybe even more, right? Because the acceleration due to gravity is 2.5 times heavier, more, right? So she's going to feel that much more force on her. Pretty cool, though, isn't it? Now think about what would happen if the planet radius is different than Earth radius. Like let's say it's like twice as much bigger than the Earth radius. Right? So if you think about it, you can square that twice as much. So now it becomes 4, right? So you take the 4 out, so it'd be like 2.5 over 4 of gravity. So a little more than a half, right? So you can do all that. So even the Jupiter is very massive because the radius of Jupiter is so huge compared to the Earth. A lot of things cancel out. Okay. All right. All right. Good. Good. I think you saw this, well, pretty much many times explained, right? Satellite motion. When Newton was, explaining his motion of, you know, planets and moon around the Earth and how it turns and goes around the planet Earth itself and how the Earth goes around the sun and how other planets, he said, it's due to gravity. Gravitational force is making it happen that way. And people were like, I don't get it. Right? So he devised this like think thought experiment. So as you imagine, you know, putting a large cannon on top of Mount Everest. Well, remember the way I did it was I built a pyramid taller than Everest. I can't do that because I'm Mr. Kim, you know. In Mr. Kim's physics class, I'm God. No, just kidding. I can build hypothetical pyramid bigger than Mount Everest and put a cannon up there, right? And then if I were to shoot that cannon with a certain speed horizontally, it has to be shot horizontally. You cannot be shooting at an angle. It has to be shot horizontally, right, with V naught. Then, depending on what that speed is, it would fall back down towards the Earth, and there it goes, the town right there. And if I put more gunpowder and shoot it with higher velocity, there goes another country. And if I even put more gunpowder and shoot at higher velocity, it may even go around halfway around the world and then hit those penguins in the South Pole. But he said there must be a certain speed when I fire this thing that it shoots out and then it just continues to go and then it falls and falls back to the Earth. But as it falls, the Earth itself curves away from the fall and it continues to fall forever. That explained how the moon goes around the Earth. That same attractive force that makes the apple fall to the Earth is what's causing the moon to fall towards the Earth and as Earth curves away from the fall of the moon. So it just keeps falling. The moon just keeps falling and falling forever. And that's how the moon goes around. It blew people's mind. It was just like total epiphany and shift in paradigm of how people thought, those who understood it. You know. So it really revolutionized pretty much how our thinking process worked. For some people, most people didn't really care. We still believe in flat Earth anyway. So it's kind of sad, actually. And that pretty much explains it. And he explained it beautifully, just using that simple thought process and thought experiment. You know? Yeah, I'm not going to spend too much time on that. But let's see how we can utilize that knowledge now. So he developed that. He said, so imagine that, and we can probably send our own moon if we want to. circling around the Earth. And he said, just make a big cannon. And then we could shoot that cannon at a certain speed. Well, what speed do we have to shoot this thing? Well, it all depends on how high the altitude of that moon has to be. So it depends on how high the altitude is, and that determines how fast you have to shoot it. So let's take a look at orbiting velocity, and then we'll talk about escape velocity too. So since we're putting this artificial satellite in a circular motion or circular orbit, right, we know it's going in a circular motion. And since it's going in a circular motion, net force is equal to MAC. We all know that. And AC is equal to V squared over R. There's only one force causing that circular motion, right? The net force is also equal to just one force, and that is the universal gravitational force. So we have to set these two equal to each other, right? We have to set these two equal to each other. So this G times, now this mass right here is the mass of the satellite, whatever is going around. And this first mass is the central mass, which is the mass of the Earth. And the second mass is the mass of the satellite. Divide that by R. Now, R, as we talked earlier, is the distance of separation between the center of the Earth to the satellite. That's R. And that R is basically the radius of the Earth plus the altitude. Remember, right? So here's the radius of the Earth. And here's the altitude. So, since we can set these equal to each other, this is what we get. Right? So set them equal to each other. And this is what we get. So look what happens to the satellite's mass. Gets canceled out. So it doesn't matter whether you put a satellite the size of a beach ball with 4 antennas sticking out, which is what Sputnik was, right? Or you could have a satellite the size of a school bus, right? You could even have a satellite size of a Death Star, right? But only thing is, you have to move it at this certain speed, and it takes ridiculous amount of energy depending on how much massive it is. That's the only reason why we don't put a Death Star up there with like laser that shoots like blows up planets. You know? So here, if you work this thing out, look what happens. One of the r's also will cancel out with this r squared. So what we get is we have v squared is equal to g times the mass of the Earth divided by r. And if we square root both sides, this is known as the orbiting velocity or orbiting speed. This r right here, of course, is the radius of the Earth plus the altitude. If you go faster than this, then what you're doing is you're escaping that velocity. Right? So this escape velocity is you're not really escaping the like forever, you are escaping to the next higher orbit. Is basically what it's doing, right? So this escaping velocity is escapes, right, to higher orbit or higher altitude. All right. Now, if you go slower than this orbit, orbiting speed, what would happen? You'll go down lower orbit. And if you keep slowing down, what's going to happen? Yeah, you'll fall back down towards the Earth, spiraling back towards the Earth. That's what happens to all these like old satellite that loses, speed. It's going to spiral back down, spiral, it's going to crash back to the Earth. Usually, it happens somewhere like in South Hemisphere, Southern Hemisphere, in like Indian Ocean or something like that, like right next to like Australia a lot of times, because that's got a lot of water there. So that's what Newton said. And guess what? They did not implement this until 1950s. And the first country to implement this, instead of using a cannon on top of Mr. Kim's pyramid, they used a rocket ship. And they used a rocket to shoot this. They used a rocket and they fired the rocket and then went up. And then when they reached a certain altitude with this V, right, all they did was they just released the satellite from the payload of the rocket and it just went around the Earth beeping. And you know who were the first ones to do it? Which country? USSR. USSR. No. Yeah, it wasn't USA. I'm sorry. It was USSR, United Socialist Soviet Republic, right? And they were the first ones to implement this. And people in the United States freaked out because they don't know what was inside that thing. And what would happen if they slow it down? It will fall back to the Earth and it could hit anywhere. And if they calculate that fall, they could reach pretty much anywhere on the planet. So they were scared when they say they, the scientists and politicians. So the United States decided to teach physics to our students, and our physics program was born. Your grandparents may remember PSSC physics. They were teaching that in college. Not too much in high school. Not too much in high school. It was too hard. But they were learning what you were learning, what you're learning now in college. And there was like rocket science. Yeah. All right. So let's take a look at some examples of how we can do the satellite, all right, kind of problem. So here we have a 5,000 kilogram satellite is moving in a stable circular orbit, and circular orbit is important, right, at an altitude of this much kilometers. So altitude is equal to, right, 12.8 times 10 to the 6th meters. So make sure you convert this, right? Convert this to meters. But that's the altitude. And just to be like different, I'm going to use this radius of the Earth given to us. Instead of 6.4, I'm going to use 6.38 just to make a difference than twice the radius here, okay? So here, R is equal to, right, the radius of the Earth plus the altitude. Therefore, the radius of the Earth is 6.38 times 10 to the 6, plus altitude, which is 12.8 times 10 to the 6. Therefore, radius of the orbiting radius comes out to, I believe, 19.18 times 10 to the 6 meters is my R. So that's good to know. So since we need to calculate the orbiting velocity, we know the sum of all force in circular motion is MAC, and we also know there's only one force that's making it going into circular motion, and that is FG. So MAC is equal to F big G. So MV squared over R is equal to G times the mass of the Earth times the mass of the satellite. I should put a satellite over R squared. Look what happens to the mass of the satellite. Boom, boom. one of the R squares gets canceled. So my orbiting velocity is equal to square root of, we already know this, but I just re-derived it, the mass of the Earth over R. So let's plug some numbers in there. So I have 6.67 times 10 to the negative 11th times the mass of the Earth is given to us as 5.98 times 10 to the 24th. And we could use 6.9, it's close enough, right? Divide that by, right, 19.18 times 10 to the 6. Whole thing square rooted, of course. So my V is equal to, just to give you a little, I guess, catch here, just in case your math is not correct in here, this is what you should get inside the square root sign. That's what you should get inside the square root. All this mess should come out to that. Okay? Which comes out to, right, 4,560.3 meters per second. This is the orbiting velocity, speed. That is approximately 10,196.8 miles per hour. So that's pretty fast. Sorry. Oh, sorry. Sorry. I got like totally into it, get zoned out. I lose myself. What time is this being? All right, so I'm going to give you guys some time to catch up on writing. All right. Therefore, now they're asking us, what's the period of the satellite? In hours. So how long does it take to make one complete revolution around the Earth? Is what they're asking. Okay? So they're really looking for the period T, which is, right, seconds per revolution. But they want it in hours. But we could probably figure it out in seconds first, and then we could convert that into hours easily, right? Well, how do we figure that out? Oh my God. Well, it's not that hard if you think about it. We know the speed. And you know the speed is equal to distance divided by time. Well, that distance traveled is one complete circumference is 2 pi r. And the period is basically time to travel that one complete circumference. Boom. Boom. So if we solve for period here, period t is equal to then 2 pi r divided by v. Now it's just a little plug and chug. So here, 2 pi r is 19.19, right? So 19.1918, I'm sorry, 19.18 times 10 to the 6, right? Meters over V, which is 4,560.3 meters per second. Notice how the meters will cancel out and giving you seconds at the top and give you seconds. So what do we get? So the period comes out to, right? I get something like 26,426.22 seconds. So if you multiply that by 1 hour is equal to 3,600 seconds, the seconds will cancel out, giving you hours. So the period comes out to 7.34 hours. This is not same thing as 7 hours and 34 minutes, right? This is actually 7 hours, right? 20 minutes and 26.2 seconds. That's what it is. Not, okay? So just in case you get confused, this is not 7 hours and 34 minutes. This is 7 hours, 20 minutes, 26.2 seconds. All right? All righty. Next. Geosynchronous satellite. Geosynchronous satellite is actually a very useful thing. Why? Well, imagine if you were like a I don't know. This is Earth during the day. This is Earth during the night. I use the one during the day. I swear that's right. All right. So I don't know if for the people at home, you can't really see this, but I'm going to see if I can turn this thing on. Can you see me? Whoa! I'm upside down. I'm in South Pole right now. Yeah, I'm in South Pole. I'm with the penguins. Oh, I'm back up in North Pole again. So, all right. So here, if you were to look at Earth right here, and if you had a geosynchronous satellite, let's say you want to broadcast something like Super Bowl all over the globe, right? If you want to put some satellite way up here that follows the Earth rotation, so that when Earth rotates one rotation in 24 hours, the satellite also rotates with the Earth and takes 24 hours to rotate it around at the same time the Earth rotates. That means the satellite will be over one spot above the Earth all the time. Wouldn't it be very, very useful if you had 3 of these Johns? Like one here, like one there, another one way back here, so you could triangulate it. So if the Super Bowl is going on right here, they broadcast that, shoot that up to this first geosynchronous satellite. Then that can be zoomed out that way and zoomed out this way, and they could broadcast it back down to all the surface of the Earth. So geosynchronous satellites can be very, very useful. All right. So okay, enough of my ugly face. Now, if you were to think about how that can be utilized, okay. So here is the Earth, and here is the geosynchronous satellite. If you put another one here, another one here, you can pretty much communicate all over the globe. Sorry. Right? You could pretty much communicate all over the globe coverage, you know. So the period of this satellite, right? So the period of this satellite is 1 Earth day. So the period is 24 hours. Maybe it's a good idea to convert that into seconds. Right? So 1 hour is equal to 3,600 seconds. So the period of this satellite should be 86,400 seconds. Altitude, we have no idea what the altitude should be. So this is the altitude right here. R, the orbital radius, R, is equal to the radius of the Earth plus the altitude. Okay. So let's figure out what altitude we have to put this thing so that we can actually have this thing turn with the Earth. All right. Again, we could start with FC is equal to, right, MAC, and then FC is equal to, there's only one force, which is F big G. Right? So if we set them equal to each other, what we get is, here's the mass of the satellite, by the way. So the mass of the satellite times AC is equal to G times the mass of the Earth times the mass of the satellite over R squared. So here, msv squared over r is equal to g times the mass of the Earth times the mass of the satellite over r squared. And of course, mass of the satellite cancels out. One of the r's will also cancel out with one of the r squareds. So my v squared is equal to g times the mass of the Earth divided by r. Now, here's the tricky part. V has to be 2 pi r over the period t. Does that make sense? Right? Well, I'm going to substitute this into this v right here so that 2 pi r over the period t quantity squared is equal to g times the mass of the Earth over r. When I square this, I get 4 pi r squared over the period squared is equal to g times the mass of the Earth over r. Don't cancel these two r's. You can't. Common mistake I see every year is that people cancel one of the r's here and one of the r's there. No. If you multiply both side by r, this gets canceled, but this becomes r cubed. Right? So 4 pi r cubed over the period squared is equal to g times the mass of the Earth. Wow, this should look familiar to you. R cubed over period squared is equal to g times the mass of the Earth over 4 pi squared. I forgot to square the pi, sorry. Does that look familiar to you? Kepler's third law. is constant. Look, G is constant. Mass of the Earth is constant. It's not going to change. 4 pi squared is constant. I mean, some student asked me, "Yo, Mr. Kim, does the mass of the Earth change?" And I'm like, well, I mean, depending on a cosmic scale, I guess if it receives some cosmic dust, it could get a little bit more. Like, it's like, no, no, but like, you know how like we're building all these bridges and buildings and stuff? Well, where are we getting those materials to build these buildings and bridges? It's like, oh, okay. Yeah, we're getting it from the Earth, right? So we're not really like making it heavier. So look at this. R cubed is equal to that, right? G times the mass of the Earth divided by 4 pi squared times the period squared. Well, well, now we can actually figure out what's going on. So what's my R? My R is equal to cube root of, right? 6.67 times 10 to the negative 11th times the mass of the Earth. It's like 5.98 times 10 to the 24th. Period is 86,400 seconds squared. You must use seconds for this. Divide that by, don't forget to put this in parentheses, 4 pi squared. If you just do divide by 4 pi squared, what's going to do is it's going to divide by whole thing by 4, and then you're going to multiply that by pi squared. So please put these in parentheses, right? So when you work this thing out, your R cubed rooted, your R is equal to, here's a checkpoint. This is just a checkpoint. So you should be getting something like this. Inside the cube root, you should get something like 7.567 times 10 to the 22nd. You should be getting this number. All this mess should be this. So that's a checkpoint, right? How do you cube root that sucker? For those of you who don't know how to use the calculator, if you go to math, there's a cube root right there, right? If you go to math, you go to this cube root right there. You click on that and you plug in, like, 7.567 EE, right? 22. And you should be able to cube root that. So when you do that, your R comes out to approximately 4.2297 times 10 to the 7th meters. That represents your orbital radius. So how much is that in terms of Earth radii? So if you divide this by, right, 6, if you multiply this by, right, 1 Earth radius is equal to, right, what do you want to use? You want to use like 6.38 times 10 to the 6 meters. You want to do that? So if you divide that by this, you get this R in terms of radius of the Earth. So if you do that, you get 6.6 radius of the Earth. Therefore, the altitude from the surface of the Earth to where the satellite should be is 5.6 radius of the Earth. So you have to stick this thing out so far out, more than 5.5 times the radius of the Earth out there. So that's really far out. So 5.6 radius of the Earth is how far you have to stick that thing out. Well, what would the speed be? What would the velocity be? Well, velocity, we already know what that is, right? V is equal to 2 pi r over the period t. We know what r is. We just figured it out. So we said 2 pi times r, which is 4.22975 times 10 to the 7th meters, whole thing over period t, which is 86,400 seconds, right? So my v comes out to 3,075.96 meters per second. And if they want that in miles per hour, all you have to do is, right, convert that. So there are 1,000 meters in 1 kilometer, and in 1 mile, there's 1.61 kilometers. If you multiply that out, I think you get something like 6,878 miles per hour as you're orbiting velocity for that geosynchronous satellite. All right. 2 more pages. Sarah, you all right? Kid, my brain's full. Now here, you are explaining to friends why astronauts feel weightlessness orbiting in space shuttle. And they respond that they thought gravity was just not a lot weaker up there. Is that true? No, not that much. It's not that weak, right? They're really feeling weightlessness is because they're falling constantly. Imagine being in an elevator and the cable snaps. You're falling. And when you're falling inside the elevator, right, you'll be floating inside there, literally, right? So when you're falling, you'll have no weight because if you try to step on the bathroom scale while you're falling, the bathroom scale will just float away from you. So you're just like, you have no weight. That's what's happening, right? So you're falling, right? But there's definitely FG, right? If there were no FG, notice it's subjunctive, then the space shuttle would not orbit. So how much force is there? Well, if I were to compare my acceleration due to gravity at 300 kilometers above the Earth's surface, this Fg has to equal to this F big G. This Fg is the mass of the space shuttle times G. This Fg is G times the mass of the Earth times the mass of the space shuttle divided by r squared. R is equal to radius of the Earth plus the altitude, which is 6 times 10 to the 6.4 times 10 to the 6, right? Plus 0.3 times 10 to the 6. That's the altitude. So R is equal to 6.7 times 10 to the 6 meters. So notice what happens. This mass of the satellite cancels out, and I could figure out what my acceleration due to gravity is at that space shuttle if it were standing still. So G, which is 6.67 times 10 to the negative 11th times the mass of the Earth, which is, I guess, 6 times 10 to the 24th. Divide that by 6.7 times 10 to the 6 quantity squared. If you calculate this thing out, my G comes out to 8.97 meters per second squared, which means it's around 9 meters per second squared, and that is about 91.5% of Earth's gravity that you'll be on the surface of the Earth. So there's plenty of gravity up there, plenty. You have 92% of Earth's gravity acting on that space shuttle when you're up there orbiting around the Earth. Right? So you got 91.5% of gravity on Earth. Okay? All right. I'm going to see if I could assign this last page as extra credit. All right? So this is extra credit. Optional. All right. Thanks for joining me, guys. Have a wonderful day.